Welcome back to the today's class. We are going to see about VI characteristics of Zener diode. Before going into that, we will discuss the properties of PN junction diode. PN junction diode reverse voltage is increased beyond a limit. Now let us consider if the voltage of the PN junction diode is the diode is in reverse biased condition. In such condition, the voltage is being reversed. At that time, the current through the junction and the power dissipation across the PN junction diode is very high. Due to this very high power dissipation across the PN junction diode, the diode junction get destructed, and if the voltage, that is the reverse voltage, is being maintained for a longer time, it damages the diode forever. Zener diode. A diode which is designed with adequate power dissipation capability to operate in the breakdown region. So, Zener diode is being used to operate in the breakdown region, which represents the Zener diode characteristics will operate in the reverse biased condition. So, we should use a Zener diode in the reverse biased condition. Such diode is known as a Zener diode. It is discovered by Carl Zener in 1934. So, Carl Zener is a physicist. He discovered the Zener diode while finding the properties or examining the breakdown region of the PN junction diode. Zener diode is heavily doped than ordinary PN junction diode. So, the amount of impurities present in the Zener diode is higher when considered with the PN junction diode. Zener diode is the silicon PN junction semiconductor device. So, all Zener diodes are made up of silicon PN junctions which are heavily doped in nature when considered with the normal PN junction diodes which are lightly doped. Symbol of the Zener diode. So, it will be very similar to that of a PN junction diode symbol. The only difference is the two sides you have to make some twist over here. So, this is the cathode terminal and this is the anode terminal. And the physical view of the Zener diode will be like this. Here, this black mark shows you the cathode terminal, and this one is the anode terminal. VI characteristics of Zener diode. Under forward biased condition, the operation of Zener diode is same as that of PN junction diode. So, when you consider a PN junction diode and a Zener diode, the forward bias region will be same. That is, the cut-in voltage is 0.7 volt, and for silicon and germanium it is maintained. Here for silicon it is 0.7 and for germanium it is 0.3 volt. When you are moving to the reverse bias condition, the point will change. Under reverse condition, the breakdown of the junction occurs. So, in the reverse bias condition, the junction started to get breakdown. The breakdown voltage depends upon the amount of doping of the semiconductors. So, the reverse biased voltage depends upon the impurities added in the Zener diode. If heavily doped depletion layer is thin, so breakdown occurs at lower reverse voltage. So, when the lot of impurities are added, that is heavily doped, then the depletion layer becomes thin, so the breakdown occurs at a lower reverse voltage. In case of lightly doped, which represent less number of impurities are added, then the depletion layer is thick, so breakdown occurs at a higher reverse voltage. So, to make the depletion region to pass, that is the electrons to pass the depletion region, you need to supply a voltage which should be higher. The voltage magnitude depends upon the thickness of the depletion layer. So here the depletion layer thickness depends upon the doping. So if you add more number of impurities, then the thickness becomes thinner. When you add lesser number of impurities, then the thickness becomes very thick and you need a very high reverse voltage to get the breakdown of a Zener diode. The breakdown voltage can be carefully designed by selecting the amount of doping. So by calculating the required voltage, you should carefully design the diode while doping it. The breakdown characteristics is significantly because it is the operating region of the Zener diode. So in case of a normal PN junction diode operates in the forward biased region, whereas in case of the Zener diodes it is going to operate in the reverse biased region, that is normally in the breakdown region. So your diode, that is the Zener diode, going to operate in this region known as Zener breakdown region. When the reverse voltage applied to the Zener diode is increased, initially the current through it is very small in microamperes. So in this case, if you see this graph, when the reverse voltage minus VR is being gradually increased, then the current which is present corresponding to the rise in the reverse voltage is very less and it is in the range of microamperes. This is the reverse leakage current denoted by I0. So this is the current I0 which is the reverse leakage current of the Zener diode. At certain reverse voltages, the current through it increase rapidly. So at this knee, a breakdown is set to occur in the device. So what happens if you increase the voltage beyond a certain limit? So say if you increase the voltage beyond this limit, what happens? A knee point in voltage occurs. This knee point is known as the breakdown. It is said to have the breakdown. The current started to increase abruptly. So this is the breakdown region and this is the knee point where the current starts to flow inside the diode. This knee breakdown is very sharp. It will be like a rectangle. The reverse bias voltage at which the breakdown occurs is called a Zener breakdown voltage, that is Vz. So at this point is known as the Zener breakdown voltage Vz. The voltage Vz can be carefully designed by adjusting the doping level. So by adding impurities, the Vz voltage can be carefully designed while manufacturing the Zener diode. Current corresponding to the Zener knee current. It is the minimum current Iz minimum the Zener diode must carry to operate in reverse breakdown region. So the minimum current, that is the Iz minimum, the minimum current the Zener diode has to carry, which should operate in the breakdown region. So in this case, the Zener diode has to carry a minimum current that is represented by Iz minimum, and this current should be present to make the Zener diode to work. The maximum current in the Zener diode that can be carried safely is Iz maximum. So this is the maximum amount of current that the Zener diode can handle. Above this current may damage the Zener diode completely. In practical circuits, to limit the currents from Iz min to Iz maximum, a variable resistors is being used. So one practical consideration to maintain the current in between the regions of Iz minimum and Iz maximum, a practical variable resistance is being connected in series with the Zener diode to achieve this condition. Now let us move into the breakdown mechanisms which are present in Zener diode. There are two distinct breakdown mechanisms happening in a Zener diode. The first one is the Zener breakdown and the second one is the Avalanche breakdown. So in case of Zener breakdown, you can see this is the Zener diode physical internal view. Here you will be having the P junction and here you will be having the N junction, and this is the depletion layer, and this is the reverse voltage which is being applied into the diode. When both sides of the PN junctions are heavily doped, the depletion layer is narrow. So you know that if the more amount of impurities added into the Zener diode, that is the PN junction, this causes the depletion layer to get narrowed. So this is the narrow thin depletion region present in the Zener diode. Zener breakdown happens in the thin narrow junction. So the breakdown of the Zener diode happens here. Reverse voltage per unit of width of the depletion layer becomes high. So if the voltage per width, that is the amount, that is the value of reverse voltage applied to the thin narrow depletion region, it becomes high. That means you are increasing the reverse voltage, which causes the depletion region to be in more stress. This establishes a strong electric field intensity which causes the electrons to break away from the atoms. This very high strong field which is created by this reverse voltage in this thin narrow depletion region causes the electrons present in the depletion region to break away from the parent atoms. Depletion region, which is insulating in nature, becomes a conducting path. So during this happens, that is the electrons which are emitted or break down from the parent atoms starts to conduct. Once it started to conduct, this narrow depletion region becomes a conducting medium when this happens. This kind of breakdown is due to creation of strong electric field density volt per micrometer is called a Zener breakdown. Due to this applied reverse voltage in the heavily doped depletion region, which is very narrow, due to the high electric field density which is represented in volts per micrometer, causes the Zener breakdown. Zener breakdown voltage is less than 5 volt. So the voltage required to break down the Zener diode will be less than 5 volt. The value of the breakdown voltage decreases as PN junction temperature starts to increase. So the voltage decrease, then the temperature starts to increase. So this characteristic is known as negative temperature coefficient. So such diodes having a thinner depletion region and having a more amount of dopant will be in negative temperature coefficient. Next we are going to see about the avalanche breakdown. When both sides of the PN junction are lightly doped, then avalanche breakdown occurs. In this case, the diode, that is the physical view of the diode, is being present in the reverse biased condition. On the same time, the PN junctions are being lightly doped. Due to this lightly doped PN junction, the thickness of the depletion region is very high. In the case of electric field is not strong, because due to this the depletion region is very high, that the electric field will not be strong. So the avalanche breakdown needs to be take place instead of Zener breakdown. The minority carriers accelerated by the field collide with the parent atom. So what happens here is the minority carriers, which is the electrons which is present in the p terminals, started to collide with the parent atom. So what happens is, because of the collision, covalent bonds are broken and electron hole pairs are generated. Due to this collision of electrons in the form of electric field which is attracting the electrons started to break the covalent bond present in the depletion region. Once the covalent bond is break down, the atom will emit its own electron and hole pairs which is generated in the depletion region. Now holes occur energy from the field and collide with other immobile ions. So in this side the holes are the minority charge carriers, and what happens is the minority charge carriers holes starts to get the energy from the field and it also collide with their parent atom and causes the immobile atoms and immobile ions. Due to this, further generation of electron hole pairs starts to occur. This process cumulative in nature and results in generation of avalanche of charge carriers within a short time. So this cumulative process which causes the lot of electrons and holes being generated inside this depletion region is known as avalanche of charge carriers, which is being formed within a very short time causes the avalanche multiplication. And this process, this mechanism of creation of charge carriers or generation of charge carriers inside the depletion region due to the field, the attraction of the field and the breaking of covalent bond is known as the avalanche multiplication. This results in flow of large value of current in the same time of reverse bias. So what happens is this avalanche multiplication creates more amount of electrons and hole pairs, which is the same as that of reverse biased condition. Due to this, the avalanche breakdown starts to occur and the depletion region gets breakdown and the electrons flow inside the diode from P junction to N junction, while in it is in reverse biased condition. The breakdown occurs at a voltage higher than 5 volt. So for avalanche breakdown, the breakdown voltage should be higher than 5 volt. The value of breakdown voltage increases as the PN junction temperature increases. So due to this property, such diodes have a positive voltage coefficient. Today we have seen about the characteristics of Zener diode, VI characteristics, and the two distinct breakdowns which are occurring in the Zener diode. One is Zener as well as the avalanche breakdown. So these types of diodes have three applications. They are being used as voltage regulators, they are used in protective circuits, and they are being used in Zener limiters. So these Zener diodes can be used to protect a circuit from dangerously high voltage being entering into the circuit. So these Zener diodes also can be used as a clipping circuits where the unwanted portion of the voltage waveform has to be removed. So these are all the characteristics and the applications of Zener diode. Thank you.